Hello, calculus. We are going to learn L'Hopital's rule, how we take the limit of an indeterminate form. If you remember, an indeterminate form is 0 over 0. So our objective, if we are given an expression that has an indeterminate form, we are going to find its limit using this rule. So let's look at the graph shown of this function right here, x squared plus 2x minus 3 all over ln x. Here is the graph. All right, if we plug in 1 into the function, we find f of 1, we get on top 1 squared plus 2 times 1 minus 3 all over ln 1. This gives us 0 over 0. That is an indeterminate form. Remember, an indeterminate form tells us that there probably is a limit there at 1. That's what this tells us. Let's review. So if we look at the graph, hey, look at the graph. Is it a good date at 1? Coming from the left, the limit is coming in at 4. Coming from the right, the limit is coming in at 4. So the graph suggests that the limit as x approaches 1 of this function is 4. Okay. The technique used to evaluate such limits is called L'Hopital's rule. It is named after L'Hopital, who lived way back in 1661 to 1704. To find the limit of a fraction that has the form 0 over 0 or infinity over infinity, L'Hopital's rule also works for infinity over infinity. You simply take the derivatives of the numerator and the denominator, and then you find the limit of that. So let's go to example number 1. If we plug in f of 1, again, we already talked about this example above, we do get 0 over 0. 1 squared plus 2 times 1 minus 3 gives us 0. ln 1 also gives us 0. Does L'Hopital's rule apply? Yes. L'Hopital's rule applies for anything that is 0 over 0 or infinity over infinity. Okay, so let's apply it. The first thing we're going to do is we're going to take the derivative. So we take the derivatives. Okay, so the limit as x approaches 1 still comes along. We take the derivative of x squared plus 2x minus 3. In the numerator, our derivative is 2x plus 2. Now, if we take the derivative of ln x, the derivative of ln x is 1 over x. Now, we see if we can do direct substitution. That means that we, of course, simply plug in 1 for x. Okay, so if we plug in 1 right here on top, 2 times 1 plus 2 is going to give me 4. All right, now let's plug in 1 on the bottom. If we plug in 1 on the bottom, 1 over 1, that gives us 1. So the answer, using L'Hopital's rule, gives us exactly what we got up here when we looked at the graph. So that is an example of a limit where L'Hopital's rule applies. Okay, again, we can't do direct substitution from the original function because when I plug in 1 in the denominator, we get a 0. We do have 0 over 0, so that tells me that there probably is a limit. Anytime you have 0 over 0, you can use L'Hopital's rule by simply taking the derivative of the top and the bottom and then doing direct substitution. All right, let's do example number 2. Okay, the first thing we do is we check direct substitution. So on top, we have 0 squared minus the cosine of 0 plus 1. On the bottom, we have e to the 0 minus 0 minus 1. Okay, on top, that gives us 0. The cosine of 0 is 1, so we get minus 1 and then plus 1. So on top, we get 0. On the bottom, e to the 0 gives us 1. Anything to the 0 power is 1. Minus 0 minus 1. That also gives us 0. So when we do direct substitution, hey, we have an indeterminate form. That tells us that L'Hopital's rule applies. Okay, so now we go ahead and we take the derivatives of both the numerator and the denominator. So we still have the limit as x approaches 0, but now we take the derivative of the numerator. The derivative of x squared is 2x. The minus 1 comes along for the ride. The derivative of the cosine is negative sine of x. And then, of course, the derivative of 1 is 0. Now we take the derivative of the denominator. The derivative of e to the x is simply e to the x. The derivative of x is 1. And the derivative of negative 1, of course, is 0. So if we simplify that, we still have the limit, of course, as x approaches 0. We have 2x plus sine of x on top, and on the bottom we have e to the x minus 1. Now we attempt to do direct substitution with the derivatives. So if I plug in 0 on top, we have 2 times 0 plus the sine of 0. On the bottom, we have e to the 0 minus 1. Okay, now when I simplify that, on top, I get 2 times 0 gives us 0. And the sine of 0 is 0, so I get 0. On the bottom, e to the 0 is 1, and then you have minus 1, so we get 0 over 0. Well, what does it mean if we still get 0 over 0 when we do direct substitution with the derivative? Hey, that means that we do it again. All right, so now we do L'Hopital's rule again. So just let me get this down. Still have 0 over 0, so we do L'Hopital's rule again. All right, and we do it from right here, from the first derivatives. Okay, so we go from here. The limit as x approaches 0, so this is the derivative again. All right, on top, the derivative of 2x is 2. The derivative of the sine of x is the cosine of x. On the bottom, the derivative of e to the x is e to the x. And of course, the derivative of negative 1 is 0. So now, when we try to do direct substitution, on top, we have 2 plus, when I plug in 0 for the cosine of 0 is 1. So we have 2 plus 1 on top. When I plug in e to the 0, anything to the 0 power is 1. Now I am getting a solution. On top, I get 3, and on the bottom, I get 1. So my solution, the answer to my limit, is 3. So this was an example of L'Hopital's rule had to be used twice in order to find the limit. So again, let's review. We plugged in 0 into the original solution, and we got 0 over 0. That tells us that L'Hopital's rule applies. We took the derivatives, simplified, we plugged in, we still got 0 over 0, and then we had to do L'Hopital's rule again. We took the derivatives, plugged in, and finally got our solution. So again, L'Hopital's rule sometimes needs to be applied more than once to get the limit. All right, let's go to example number 3. Okay, example number 3, we have a function right here, x squared times e to the negative x. We're going to find this limit both by using the graph and by using L'Hopital's rule. So if we look at the graph, as x approaches infinity, that means the x's are getting bigger and bigger. So on the x-axis, what is the graph doing as you're going farther and farther to the right? Well, as we follow this curve going farther and farther to the right, that's getting closer and closer to 0. So using the graph, the limit as x approaches infinity is 0. All right, now we are going to use L'Hopital's rule. Now, when I plug in infinity, what you have to think about is you're plugging in a really, really, really big number. So let's practice this. We're going to plug in infinity here. So we're going to have infinity squared. And then it's going to be e to the negative infinity. E to the negative infinity. So I'm just plugging in infinity. I'm thinking about plugging in a really, really big number. Okay, if I plug in a really, really big number and I square it, hey, guess what? I still have a really big number, so I'm going to represent that with infinity. Again, if I take a really big number and square it, I still have a really big number. Now, over here, if I take e to a really, really big negative number, that's going to be getting closer and closer to 0. Again, if I take e, which is 2.718, and I raise it to a really, really, really big negative number, that's going to get me closer and closer to 0. So, we don't have 0 over 0 yet, and we don't have infinity over infinity yet. So we can say, at this point, L'Hopital's rule does not apply yet. Okay, but now what we can do is we can rewrite this so that we can use L'Hopital's rule. So we're going to rewrite this as the limit as x approaches infinity. I'm going to keep x squared on top, but because this is a negative exponent, I can put that down on the bottom, and instead of e to the negative x, I can rewrite it as e to the positive x. Now, when I do direct substitution, I get infinity squared all over e to the infinity. That gives me, if I take a really big number and square it, I still have a really big number. I'm going to represent that with infinity. And if I now raise e to a really, really big positive number, that's going to give me an even bigger number. So that's going to be infinity over infinity. So now this right here, that tells me that L'Hopital's rule does apply now. Okay, so now we're ready to go. Now we take the derivatives. So we still have the limit as x approaches infinity. On top, if I take the derivative of 2x right here, or excuse me, if I take the derivative of x squared, I get 2x. On the bottom, if I take the derivative of e to the x, I get e to the x. Now I do direct substitution with the derivative. So again, if I plug in a really big number and I multiply it by 2 times infinity, that still is going to give me a really big number. If I plug in infinity in the denominator and if I take e to a really, really big number, hey, I still have a really, really big number. So again, when I plugged into the to the derivatives, I still have infinity over infinity. So now I must do L'Hopital's again. That means I simply take the derivative. All right, so we do the derivative again. So I still have the limit as x approaches infinity, but now I take the derivatives. The derivative of 2x is 2, and the derivative of e to the x is e to the x. Now I do direct substitution with those derivatives. So I have 2 in the numerator. On the bottom, if I take e and raise it to a really big number, infinity, that gives me 2 over a really, really big number. Again, if I take e and raise it to a really, really big number, I get a really, really big number. And if I take 2 and divide it by a really, 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 really big number, I'm going to get 0. And that's exactly what I got up here when I looked at the graph. So this is an example of a problem that you have to apply L'Hopital's rule twice to get the solution. All right, I want you to try examples 1 through 4 on this note sheet and then check back and we will go through them. Okay, example number 1. The first thing you do is you do direct substitution with the original function to see if L'Hopital's rule does indeed apply. So when I take f of 0, on top, I get 2 times the sine of 5 times 0, and on the bottom, I get 3 times 0. That gives me 0 over 0. So that tells me that L'Hopital's rule does apply. So now I take the derivatives. So I still have the limit as x approaches 0. On top, the 2 comes along for the ride. This is going to be a chain rule. The outer function is sine and the inner function is 5x. So the derivative of the outer is cosine. The inner as is 5x. And the derivative of the inner is 5. On the bottom, if I take the derivative of 3x, I get 3. If I simplify that, I have the limit as x approaches 0. I have 10 times the cosine of 5x on top, all over 3. Now, when I do direct substitution, let's see what happens. I have 10 times the cosine of 0, because 5 times 0 is 0, and on the bottom I still have 3. Okay, well, we know that the cosine of 0 is equal to 1. This right here is equal to 1. So on top, we end up with 10 times 1, which is 10. On the bottom, we have 3, and there we have it. All right, you can always check your work by looking at a graph, finding the limit using a graph. There is example number 1. All right, example number 2. The first thing we do is we plug in infinity in for x to see if L'Hopital's rule does apply. So on top, let me get this down. We're going to do f of infinity. So that gives us 3 times a really big number plus 17, and on the bottom 4 times a really big number minus 11. Well, that's going to give us 3 times a really big number plus 17 is still a really big number. And on the bottom, if we take 4 times a really, 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 really big number and only subtract 11, that's still going to be a really big number. So there you have it. This direct substitution into our original function gives us infinity over infinity. That means we can use L'Hopital's. Yippee. Okay, so now we go ahead and we take the derivatives. So we have the limit as x approaches infinity. On the top, the derivative of 3x is 3. And the derivative of 17 is 0. On the bottom, the derivative of 4x is 4. And the derivative of negative 11 is 0. So when we take the derivatives, we get 3/4. Now, if I take the limit as x approaches infinity of 3/4, well, guess what? Now we use the limit property. The limit of a constant is that same constant. So our answer is 3/4. So you just have to remember that the limit of a constant is that same constant. All right, the limit of a constant, just any number, is that constant. All right, that's example number 2. Example number 3. Again, we first do direct substitution to see if L'Hopital's rule applies. So if we take ln1 on top and 1 minus 1 on the bottom, ln1 gives us 0. 1 minus 1 gives us 0. There you have it. 0 over 0. Hey, we know L'Hopital's applies. Okay, so now we go to work and we take the derivatives. So the limit as x approaches 1. Okay, the derivative of the numerator, ln x, is 1 over x. The derivative on the bottom, the derivative of x is 1. And the derivative of negative 1 is 0. So our derivative gives us 1 over x, 1 over x over 1. So that, if we simplify, now we can do, well, we don't even need to simplify. We can do direct substitution as is. So now we do direct substitution into the derivatives, and we get 1 over 1 all over 1, which is 1. Yippee! How easy is that? And there's our answer. All right, last but not least, example number 4. Again, we do direct substitution to see if L'Hopital's rule applies. So on top, we get ln1 minus 1 plus 1. On the bottom, we get 1 squared minus 2 times 1 plus 1. All right, well, ln1, this gives us 0. So negative 1 plus 1, we definitely get a 0 on top. On the bottom, 1 squared is 1. 1 minus 2 is negative 1. -1 plus 1 gives us that 0. So there we have it. This right here tells us that L'Hopital's applies. All right, so now we use L'Hopital's rule. We take the derivatives. So we still have the limit as x approaches 1. On top, the derivative of ln x is 1 over x. We keep going. The derivative of -x is -1. And the derivative of 1 is 0. All right, now we go to the denominator. The derivative of x squared here is 2x. The derivative of -2x is -2. And the derivative of 1 is 0. So there is our derivative. All right, so now we do direct substitution into those derivatives. All right, so we get 1 over 1 minus 1 on top. On the bottom, we get 2 times 1 minus 2. Hey, that gives us 0 over 0. So this tells us that we must do L'Hopital's again. All right, so we do the derivatives again. So we still have the limit as x approaches 1. On top, in order to take the derivative of 1 over x, I'm going to go down here. Let's review. 1 over x is the same as x to the -1. So when I take the derivative, I get -x to the -2. And then if I rewrite that so that I don't have a negative exponent, I need more room there in my thinking box, I get -1 over x squared. So that is the derivative of my numerator right here. The derivative of 1 over x is -1 over x squared. I keep going up on top. The derivative of -1 is just 0. So now I go down to my denominator. The derivative of 2x is 2. And the derivative of -2 is 0. So when I take the derivatives again, I get this right here. Now I go ahead and I do direct substitution. All right. On top, I have -1 over 1 squared. And on the bottom, I have 2. And that gives me a solution of -1/2. And there is the solution. Okay. Ooh, I guess we're doing green. All right, calculus. This is a tough topic to do remotely. Please go through these notes. Please work on the practice worksheets and be in touch. Catch you on Google Meets. Goodbye, Calc.